looking at it.
Well, yeah, that's probably true. Let's see here.
I also already have an idea of what I did, so like
Did I post a solution yet? I think I did.
Yeah, you did.
Cool.
No, you posted the test. Thank you.
There you go. Let me begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, I thank you for this class, these students. Just ask you to bless our time together, Lord. In the name I pray, Lord Jesus. Amen. All right, so, oh yes, the attendance sheet. Just to be clear, the way attendance sheets work is you check one box per class meeting.
I will say I have not gotten the attendance sheet yet this semester. It's never made its way back to me.
Well,
That's all Shane's fault. What is Shane's fault? She doesn't do. What did Tyler do?
I don't know what happened, but
Oh.
I'm not sure what's happening. But last time, you may recall, if you were here or if you watched the video, that we defined the complex integral. And we also worked out a result. In particular, we proved that if, and I'll call this FTC2, that if f prime of z is equal to little f of z on and near C, which goes from P to Q, then the integral over C of f of z dz is simply equal to f of P minus f of Q. You probably recognize this theorem from Calculus 1, right? But the difference, of course, now is that we're talking about a complex function, right? And so perhaps an interesting example of this, which I don't think I did last time, is as follows. So, oh, that's dead. Wow, it was really, really far off. So let us look at the integral of like dz over z over, let's say, c epsilon. And the c epsilon I have in mind is going to look like this. All right, so so let's see here, counterclockwise, c epsilon. And all right, so the parameterization of this thing is going to be z equals like r e to the I pi, no, see, I'm thinking here, e to the I, oh, goodness gracious, maybe t plus epsilon, is that right? Minus pi less than t less than pi. Let's see here, that makes this curve go from where to where? So like this point right here would be z equals r e to the I pi, or minus pi plus epsilon, right? Yeah, and this one up here would be z equals r e to the I pi plus epsilon. All right, so a little bit above and a little bit below the what? This thing right here is the what? This is the branch cut for what? The usual logarithm, right? Yeah. So if you look at this then, in and near this curve, we have that d dz of log z is 1 over z, right? Yeah?
Would pi plus epsilon be outside of the range? Or, sorry, the domain. No, wait, the range. I'm wrong.
So I guess I want to minus epsilon then. Would that fix it?
I think it would still be outside of the bottom.
Huh. All right, so we'll make the bottom.
Could you like put one in your parameterization?
Yeah, let's just put it here. And there's probably another way to do it, but fine. Maybe 2 epsilon if I do that. Then this is curses. These details are not interesting. So we get minus pi plus 2 epsilon, so minus pi plus epsilon, right? Which would be like that's what we want, right? Okay, great. So on that, you know, almost circle arc, right? We do have an antiderivative, which we called last time a primitive. And as such, we can apply FTC2, and we get, you know, the log of, r e to the I times minus pi. Did I do that the right way? Yeah, okay, so that's the endpoint. R e to the, I can't do math. Pi minus epsilon up here, minus the log of r e to the I times minus pi plus epsilon down there, right? Which is the natural log of r plus I times pi minus epsilon minus the natural log of r minus I times minus pi plus epsilon. The logs cancel, and we get 2 pi I minus 2I epsilon, I think. Right? Do we agree? Disagree? Ambivalent? All right, so then what happens as epsilon goes to 0? If you think about it, the circle of radius epsilon is going to go to the full circle of radius r, right? Like the full thing, all the way around, right? And we proved last time, I think my example 1, that if you integrate over the circle of radius r counterclockwise, dz over z, you get 2 pi I. We proved that last time, directly from the definition of the complex integral. And so this is another way of understanding that. And also, as I have told you guys numerous times, this angle jump is not just something to kind of like gloss over and ignore. It's the central issue of the course. It's where everything interesting is coming from, almost, I would say. Isn't that bizarre? That some of the more interesting aspects of complex analysis really just go to the angle degeneracy that you learned about in pre-calculus. It's weird, but it is the case. All right, so that's that. Thought I'd show you that example. Now I'm going to jump over here and talk about Cauchy's theorem. This is one of several Cauchy's theorems. The one we'll start with here. So this is my theorem 7.2.9. And this is called Cauchy's theorem. There are other Cauchy's theorems, but they're typically, there's like extra language added. Like there's Cauchy's integral theorem we'll talk about today, and also Cauchy's generalized integral theorem we'll hopefully talk about today. Those are different theorems due to Cauchy, but both of those also rest on this theorem, which I'm going to write out here. And so Cauchy's theorem states the following. If f of z is holomorphic and continuously differentiable on D and extends to the boundary of D as well, then the integral around the boundary of D of f of z dz is equal to 0. Now here, the boundary of D is the oriented boundary of D, where the inner boundaries are taken to be clockwise, whereas the outer boundaries are taken to be counterclockwise. Let me draw a picture. So here D is assumed to be a domain. So here D is a domain. What's a domain? It is a what? An open connected set. That was our definition, right? So an open connected set is a domain. That's what D is. The boundary of D, all right, is defined by the usual rules of calculus 3. So like the boundary of D goes like this out here, all right, and it goes like this in here. So clockwise on the inside, counterclockwise on the outside. All right, and D itself is the region between those. So, I mean, the boundary of D technically is the boundary of D is the not the dotted line, but the filled in line, right? And D itself is kind of like, well, I can't shade on a, you know what I'm trying to, this stupid whiteboard piece of garbage. Sorry, we have a chalkboard. You can't teach math in this stupid building. All right, did I ever turn my mic on? Let's see here. Let's see here. I did. All right. So anyway, this is the context. The open connected set. This is the theorem. So I will give you a proof in not the most efficient of notations. I will give you a proof in terms of, no, I'm going to do it in the best notation possible. Here we go. So we have the integral over the boundary of D of f dz. But that is equal to the integral over the boundary of D of f dx plus I times dy, right? Because as we talked about last time, dz is dx plus I dy. That is a notation which we can meaningfully use in here. All right. So this is equal to the double integral over D of, oh, I seem to have lost an f over here. That's not good. IF, there we go. So here we go. Partial x of IF minus partial y of f dA. where A is the area, infinitesimal element. Now, do you guys know what I'm doing?
Green's theorem, right?
Green's theorem, yeah. So here's Green's theorem in usual calculus 3 notation. Integral of p dx plus q dy over the boundary of D is equal to the double integral of partial q partial x minus partial p partial y dA over D. And this is good for regions with holes, provided you make this convention for orienting the inside boundary clockwise, the outer boundary counterclockwise. This can be proved. Should be proved in Calc 3. So this is Green's theorem, right? So what I'm claiming is that I can do the same in the complex. I can think of this as P, and I can think of, oh my bad, up here. I can think of this as P, and I can think of this here as Q. And I'm claiming that Green's theorem naturally generalizes to complex componented, it's not a word, is it? Vectors with complex functions as components. So you're like, well, are you sure that's true? Well, I don't know. That's why I made it homework. So you guys will show that this still makes sense if P and Q are complex. That's the complexified Green's theorem. This is not a hard homework. You literally just write down Green's theorem twice and add it. That's all there is to it. But now that we have this, because I trust you guys to do your homework, proof by homework is there's proof by authority, there's proof by, there's been different methods of proof, but I think proof by homework is maybe the most enjoyable method. Let's see here. So integral over D of I of partial f partial x minus partial f partial y dA, right? But you guys tell me, what's the story here?
0.
That is 0. Why? That is 0 because this right here is 0 by Cauchy-Riemann. So there you go. That's Cauchy's theorem. That wasn't bad, was it? So you could also do this by writing f equals to u plus iv, and then writing dx as dx plus I dy, and multiplying it out, and then using the ordinary Green's theorem separately on the real and the imaginary part. But then you wouldn't have homework to do. It's no fun. So, yeah. Notice something here is a little bit, so this, I should mention, this right here, continuously differentiable, what does that mean? That means that the derivatives, the partial derivatives themselves are continuous functions. This is what we mean by continuously differentiable. It turns out that that assumption is superfluous. It's, I can't say that word either. It's not absolutely necessary. We will prove that if you have the functions holomorphic on the domain, it's automatically true that the derivative has to be continuous. So there are no once differentiable but not, continuous with continuous derivatives. It's automatically true that the derivative will be continuous. Yeah.
So if they only have to be holomorphic, why does Cauchy's theorem state that it has to be continuously differentiable?
Just start the question again.
So if they don't, if the function is holomorphic, then why do we, and we don't need it to be continuously differentiable as we'll prove?
Oh, I need it for the proof I'm giving here right now. See, the only reason, so the reason I need it here is in the preconditions for Green's theorem, you need that these derivatives are continuous for the usual proof of Green's theorem at least. And so that's the sense in which I'm using the continuous differentiability. It's a precondition necessary for implementing Green's theorem. So, but what I'm saying is that even if I didn't say that there, we have a later theorem which stands independent of the proof of this that will imply this automatically from that. So it's So there's that. Next up, we have Cauchy's integral formula. All right, I'm going to put that over here, I think. This board's nicer. I don't like being behind the lecture, but I also don't like that board. Wait a minute. Take that. Thanks, Shane. So Cauchy's, oh, by the way, fun fact. Cauchy's theorem, that's also true in A calculus. If you define an integral over an algebra, turns out that that's true. It's actually not a theorem that's special to complex analysis. It's still true in hypercomplex analysis. If you define the integral over such an algebra. That is not true about the theorem I'm about to write. The theorem I'm about to write is native to complex analysis. One of my standing problems in A calculus is to find out other contexts in which this is still true, or some generalization thereof. So here we go. Theorem. This is Cauchy's integral theorem. I can't spell. Cauchy's integral theorem. Here we go. Let D be bounded domain all right, with piecewise smooth boundary if f of z is holomorphic on D with continuous f prime of z on D, and f of z and f prime of z extend continuously to boundary of D, then for each z in D, we have the following. F of z is equal to 1 over 2 pi I integral over the boundary of D, f of w dw divided by w minus z. This is weird. I just have to say, like, this is a weird theorem. Like, the first time I saw this, I was like, what are they saying? What does this even mean? You know? But there it is. This is Cauchy's integral theorem. So what I mean by extend continuously, guys, is if I go back to my picture, I'll just give it a single hole, that will suffice, right? Then what I mean by extend continuously is that if you can imagine going a little bit beyond, which means a little bit inside the inside and a little bit outside the outside, right? Right, so like, you see what I'm saying? All this. That U is open and the boundary of D is contained in that open set. And on that U, f and f prime are continuous. That's what we mean by extends continuously. We were saying that you can get a little bit past the boundary curve and still have the formula make sense in the continuous sense. All right, so here's the proof. so we assume the preconditions of the theorem. We fix a point Z and D. I regret making my picture so cluttered. Let me unclutter it. Well, you got this idea? All right, good. I need a less cluttered picture. So we're going to fix a point Z and D. So here's my picture. I'll make a little hole over here just for the sake of whatever. So here's Z, let's say. Fix a point Z and D. D is open, hence Z is interior. Thus we are free to choose an epsilon for which the disk of radius epsilon is a subset of D. Let's see here. So I define All right, so we've got some epsilon there. Definitely such a neighborhood of Z exists inside D, right? And then I define D sub epsilon. There we go. D sub epsilon equal to D with that disk removed. So W in C such that the modulus of W minus Z is less than or equal to epsilon. So let me make that not dotted, but so what I've just done, right, is I've deleted this epsilon disk around Z, right? This right here is this. We just cut it out, right? So what can you guys tell me about the remaining d epsilon? What is this? I'll tell you what it is. It's an open set, right? Because, you know, it doesn't include that boundary. So it's essentially fuzzy there, right? And it's also connected by virtue of the fact that D is connected, right? So this is an open set. In fact, it's a domain, truth be told, right? It's an open connected set. All right. And so notice that the boundary of d epsilon, right? It is what? It consists of the boundary of D unioned with what I'm going to call gamma epsilon with a minus on it for some reason. Oh, I know why the minus. Why the minus? Because in my notes, gamma epsilon is the, I think I need to put a, I mean technically, let me put a Z here just to emphasize where that is. So here this is the clockwise oriented, you know, if we take W minus Z equal to epsilon, all right? So it's the clockwise oriented red circle there. You see why we have to do that? Because it's the interior, I can't do clockwise, goodness gracious, clockwise. Yeah, okay, wait, yeah. So like this. On the other hand, the boundary of D counterclockwise, right? Because it's the outside. All right, so far so good. Now, let G of W equal to F of W over W minus Z. And you guys tell me, what's G prime of W equal to? How about this? It's F prime of W over W minus Z minus F of W over W minus Z squared, right? So what I did right there is the product rule. Right? And we're differentiating with respect to W, so there's no like extra minus there. Any questions? So is this holomorphic on d epsilon? I mean, I would say, you know, observe that G of W is holomorphic on this. Why? Where does this get? So first of all, we are assuming that F and its derivative, right, are holomorphic on and near D and its boundary, right? So these are good. And this could get us into trouble if W were equal to Z, but it's not by construction, right? W is not Z because it's away from the edge there. So what does this mean? So this means that we can apply Cauchy's theorem, right? We can apply Cauchy's theorem. And what does Cauchy's theorem tell us? So we have that the integral of G of W dW over, you know, the boundary of d epsilon is equal to, well, it's equal to 0. That's Cauchy's theorem, right? But on the other hand, it's equal to the integral over the boundary of D of, you know, G of W dW minus the integral over, or plus the integral over gamma epsilon minus. Now here I'm using the linearity property of the integral, namely that if you have a curve which is the union of two curves, then likewise we get the sum of the two integrals which form the whole curve, right? So we have that property. So what's this tell me? So this obviously tells me that the integral over the boundary of D of G of W dW is equal to like minus the integral over this thing. And let me just go for the clockwise oriented. So gamma epsilon of Z G of W dW. So this thing is counterclockwise oriented, whereas this one was clockwise. And that's where I got rid of the minus from moving it to the other side. Because the integral, like the line integral from calculus 3, is oriented. So if we reverse the curve, we get a minus. All right? So then what? Then what can we say? Well, then I need to calculate this contraption on the right-hand side here. And I will have to rely on yet another homework, which I may or may not have assigned to you guys. So, I don't know. So let's work on that piece. I guess I can always add homework, right? Not allowed. All right, so, oh man. So next up, we're going to look at, and I'm going to get back into the details of what G is, all right? So G is what? G is f of W over W minus C. So we'll look at the integral over gamma epsilon plus of Z, which I don't put the plus on. I got a plus in the notes, but I'm deleting it here. F of W over W minus Z. And my claim from the notes is that that's actually equal to the integral from 0 to 2 pi of f of Z plus epsilon e to the I theta divided by epsilon e to the I theta I epsilon e to the I theta So far I haven't used the notes actually. What am I doing right here? I actually haven't used the notes yet. Here I'm just using the definition of the complex integral. All right, so like what's the parameterization of that curve? See, this has, like, you can put z equal to epsilon e to the I theta for 0 less than or equal to theta less than or equal to 2 pi. And if I do that, dz d theta is I epsilon e to the I theta, which gives me dz is I epsilon e to the I theta d theta, which is where this is coming from. All right? And I think I messed that up. So I was supposed to do what? Sorry, it's hard for me. Z is fixed here, so W is the variable. So that's W dW. And this was supposed to be W Z plus that. All right. Then W minus Z is what? Right? So that's the denominator. All right, and then W is, well, Z. All right, there it is. So that's just the definition of the complex integral. And as such, this leaves us with what? The epsilons, they be canceling, and I think we get I, the integral from 0 to 2 pi of f of z plus epsilon e to the I theta d theta, which doesn't look particularly helpful. Oh, I lost my d theta. Ooh. What? Oh. I'm an idiot. I'm sorry. My eyes are just skipping past what I was writing there. Look what I've done. I've done something sneaky. I've multiplied and divided by 2 pi. See, I put a 2 pi out here. And I put a 2 pi over here because in your homework you show that this is f of z. And this result is called the mean value theorem, or well, mean value property, let's say, for, you know, f of z holomorphic on D. It's an interesting result. What it says is that the average of a holomorphic, the average values of a holomorphic function around a circle are just given by the value of the function at the center of the circle. So it's a kind of peculiar property. It's another way of characterizing holomorphic functions, which I didn't. Sometimes I cover this like before test 1. I just did in this semester, but so I think it's a homework problem for you. It's not especially. It's a kind of quirky homework problem. It requires a certain like sleight of hand. I think it involves switching the order of differentiation and integration. So there's some kind of sneaky analysis in here. But if that is the case, I'm sure there's a hint in the homework to tell you what to do there. In any event, there it is. And so once you know that, therefore, the integral over the boundary of D of f of w dw over w minus z is equal to, apparently, 2 pi I times f of z. And that, you know, up to how you write it, of course, this also says what? F of z 1 over 2 pi I integral over the boundary of D of f of w dw over w minus z. Now, so there you go. That is Cauchy's integral formula. Let's rewrite it with a different letter. right? Let's write it like this. So f of z naught is equal to 1 over 2 pi I integral of f of z dz over z minus z naught. Like, there we go. That's just, to me, that's a little bit more natural, a way to formulate the theorem, because I like to think of z naught as a fixed point, and I like to use z as the variable in here, typically. But nevertheless, it is traditional to at least start by writing Cauchy's integral formula as we did. Any questions? I'll show you some applications of this in a minute, but before I do that, I want to show you how we can derive Cauchy's generalized integral formula. Check this out. So if this is true, what do you think f prime of z naught should be? Shouldn't it be 1 over 2 pi I, the integral of d dz of f of z over z minus z naught? Oh, rats, that's why we use z and w. Curses, now I know. Well, anyway. It's not wrong, but it's not helpful. Dummy. All right, f prime of z, 1 over 2 pi I. I'm going to stick with my w. Integral over the boundary of d dz of f of w over w minus z. Now, suspend your disbelief that I can just do that I can just permute the order of integration and differentiation. All right? But suppose I could. If I could, then I'd have this, which would give me what? Can you differentiate that? Now this time I have to worry about the chain rule. I'm differentiating with respect to z. When I differentiate this with respect to z, I have the reciprocal, right? So I have the minus, I get minus 1 over w minus z squared, but then I have to multiply by the derivative of the inside, which gives me an additional minus 1. So minus minus gives me a plus. That's why I just have this. And if you can do it once, why not do it again? Like, what's f prime prime of z? Again, we're going to assume we can bring the differentiation inside the integral. What's that give us? Well, it gives us, apparently, it gives us a 2 over 2 pi I integral boundary d f of w dw over w minus z to what power? We worked our way up to a 3. Why do something 2 times when you could do it 3 times? F prime 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 of z, 2 over 2 pi I, integral over the boundary of d of d dz of f of w over w minus z cubed. This is not in the notes. No note taker. Oh, are you taking it? Did I get it? Still not writing anything. Is this in the notes?
No. Yes, but there's 3 times on it.
Ha! You have to write this down. So, let me switch back to a more seeable marker. So what happens? We get a 3 times 2 over 2 pi I integral over the boundary of d f of w over w minus z to the 4th power dw. Is the pattern clear yet? So what can you tell me? What's the mth derivative of z equal to? So w minus z to the what? M plus 1 down here. And m factorial over here, yeah. And there you go. That is the generalized Cauchy's integral formula. Yep.
So if you ask us to derive this on the next test, is 2 derivatives enough?
I mean, I don't know. It kind of depends on how I asked it, I guess. But the truth is that if I was to ask, oh, that's right, engineers. Well, let me show you what I would have wanted you to prove in a time now forgotten.
I was going to, but
Why did you make so hard?
what do you mean? I was writing other things. I mean, I could derive it. I could take the derivative. Differentiate derivatives.
But the smart way to do it would just be to say m equals 0 is true by Cauchy's integral formula, which I've already proved on this test. And that was a joke, maybe. No, it wasn't. I think Cauchy's integral formula is not too hard to prove. I've asked that before. I'm not joking. But if you knew Cauchy's integral formula, you could just use an argument by induction. Assume it's true for m, prove that it's true for m plus 1. It probably is not. That's not hard if you assume that you can pass the derivative inside the integral. That is something I later justify, I think, in here. It can be justified nonetheless. Although that kind of begs the question because the things which justify it actually use Cauchy's integral formula. So it's not exactly the greatest logical argument typically to use what you're trying to prove something. You know, it might work for politicians, but it doesn't usually work in a math class. But anyway, let's see here. So this is the actual proof of the Cauchy's integral formula. Not Cauchy's integral formula. This is the m equals 1 case. So for m equals 1, you calculate the difference quotient of f, and I use Cauchy. I think I'm using Cauchy's integral. Cauchy's integral formula to do two different pieces, and then I'm putting them back together and simplifying and taking the limit, and that's the m equals 1. So like you can actually just look at a difference quotient, apply Cauchy's integral formula twice, do algebra, take the limit, there it is. This is a little bit uglier to do the generalized one. So I had to do this algebra, and then to take the difference of the mth powers, I get this, which gives me that. And then I use induction on both of those pieces separately, and then take the limit. And in so doing, oh man, no, the double scrolling, it got me all the way over to power series. Goodness gracious, what has happened? Oh. Ay. Oh man. Oh, here we go. So the point is then you make an argument by induction, and then take the limit, and voila. All of this without passing the derivative inside the integral. So these arguments do not use that sleight of hand. But that sleight of hand makes deriving Cauchy's integral formula simple, absolutely trivial, really. Just a calculation that we just did, right? Like I hope you're not seeing this as hard. This is not hard. This is like, I mean, just differentiate to get a new theorem. That's an incredible deal. Like, we never get that deal anywhere else. You just differentiate to the next theorem. That never happened. Did it ever happen? I don't think it ever happened. I don't remember ever doing that in another course. I just differentiate a theorem and get another theorem, you know. So that's kind of neat. All right, so now that we know Cauchy's integral formula, we should look at some examples of it. So like here's a good example of it. Suppose you're integrating sine of 2z over z minus I to the 6th power. You don't want to do that directly. You just don't, okay? And the good news is you don't have to, because you can apply the Cauchy's integral formula to say that's 2 pi I over 5 factorial, the 5th derivative evaluated at I of sine of 2z. But that 5th derivative is pretty easy to calculate, because we can differentiate sine all day long, not a big deal, right? That gives us minus 32 cosine of 2i, which you guys know is cos of 2. And so there you go, 8 pi I, minus 8 pi I over cos of 2 divided by 15. That's that integral. Whoa. We just calculated an integral by differentiating. Do you remember ever doing that in real? No, that only happens here. There's this weird confluence between differentiation and integration and complex analysis that allows us this kind of just insane calculation, really. Now, my next example, we're looking at z to the 4th plus I, which we can factor, right? Well, at least one of you could factor. Sorry, too soon. I just, the incuriosity about what that large number was by most of you, like, I just don't get it. You should know me by now. It's obviously 42 to the 4th power. I mean, come on. So here is what this is, which is that. Now the thing about this is this circle, the picture up there is relevant. Let's look at the picture. So the picture, I have graphed all 4 places where the denominator, 1 over z to the 4th plus I is 0. So 1 over to the z to the 4th plus I is 0 at the green dots, right? And also the red dot. But only the red dot is inside the circle of radius 1 centered at 1. So when I apply Cauchy's integral formula, in this case, just the m equals 1 case, all right? I only have to pay attention to the place where I have division by 0 inside the circle. The rest of that is a holomorphic function inside the circle and nearby. So like everything here, except for the z minus e to the minus, everything except for this piece, like all of this is well behaved inside the blue circle. Only this guy is troublemaker. So we basically think about 1 over all of this is our f of w, and think about this as like, oh, I got it. So here I need the formula I erased because I'm doing integral over dz. You know, now that we got through the derivation, how about this? Z naught z minus z naught dz. There you go. So this is, or more to the point, the integral of f of, oh man, that was f of z. Okay, it's fine. Integral of f of z dz over z minus z naught to the m plus 1 power is equal to 2 pi I over m factorial in the mth derivative evaluated at z naught. Like, this is how we actually use the theorem to calculate things. And maybe it would be a good idea for us to just take a second and to reindex the theorem, right? Let's maybe take a second to reindex it. What do I mean by that? If I erase this m plus 1 down here, right? If I make this an m, then what happens? this becomes right? So m equals to 0 is Cauchy's theorem, because it's just the integral, assuming that this is 0, assuming that like the minus 1th thing is 0, giving that as a definition. So if you want to think about the minus 1th derivative as being automatically 0, you could think about this being Cauchy's theorem, not the integral one. M equals to 1 is Cauchy's integral formula, right? And then m greater than or equal to 2 falls under this, I would say. So I'm using this over here, the m equals 1 case, to do this calculation. I'm identifying f of z is everything except for the thing that's dividing by 0 there. Everything except for the troublesome piece. So notice that this is not present down here, right? I've got everything. Oh, there's an I there. There's a plus, not a minus. There's an I. Okay, so this guy is not present, and that's why I'm evaluating there, because that's the z naught. So I evaluate there, and that does the integral, just like that. Just like that. All right. So, excuse me. One last point before I forget. Notice that if f of z is holomorphic with continuous derivative f prime of z, then we have infinite complex differentiability by these formulas. Because if we have the first derivative, we can get the we can get the second, we can get the third, and right here, the formula is right here. Here's how you calculate the mth derivative. So one complex derivative implies as many as you like. This does rest on the assumption that we have continuity of the complex derivative. It does rest on that. And so I need to prove that to you guys. So we'll come back to Leibniz's theorem next time probably. I want to focus on these deeper theorems here, since this kind of fits together. So this is Morera's theorem. Morera's theorem says the following. It says f of z, a continuous function on a domain U, all right? Then if the integral around every closed rectangle contained in U, sides parallel to the coordinate axis, is 0, then f of z is holomorphic and we get continuity of the derivative. So what this theorem says is holomorphic. In other words, holomorphic means that the complex derivative exists on the set, right? But that does not automatically mean that that derivative as a function is continuous. That's the distinction. Like, I know this kind of washes past people because you get used to, like in Calculus 1, we teach you, well, if it's differentiable, it's continuous, right? But we're talking about the function. Differentiability of the function implies continuity of the function. Differentiability of the function does not imply continuity of the derivative of the function. That's a separate issue. So what we're talking here is the differentiability of the derivative of the function. That's what it takes for it to be continuously differentiable. So the proof goes like this. We take a little rectangle and you break it into like two paths like this. And I may need to use a theorem I didn't prove for you guys. Uh-oh. Well, if that's the case, we'll go back to do that one. But anyway, so the vanishing of the rectangular integral allows us to exchange the lower path for the upper path, right? So like, if the integral around the loop is 0, then the integral of the red piece and the integral of the blue piece have to be equal, because remember, we can take the loop and divide it into the upper and lower